the organizer and the member of the program committee, to all of you for coming, and a special thank to Bob for his kind hospitality in this lovely Oxford. So I don't think I need to spend many words in motivating this talk, because here the audience is very sensitive to this problem. Let me say that the problem is actually a big program. It's the same program as Alex is involved in, and Rainer, and maybe other people here. We want to derive quantum mechanics as a generic probabilistic theory plus some principle. Let me call this principle for short the principle or a principle of the quantumness, as opposed to the principle of relativity, just to have a single word for this principle. What I mean is that quantum mechanics currently has the same status of the Lorentz transformations before the advent of Einstein relativity, in the sense that, as you know, you can derive the Lorentz transformation from the principle of relativity, namely that all physical laws are invariant with the reference system and a bound for speeds, for velocity. And you can derive the Lorentz transformation this way. Quantum mechanics is a kind of set of Lorentz transformation, mathematical framework without a principle, and we want to derive an analogous kind of principle for quantum mechanics. If you think about the principle of relativity, the two principles of relativity are not any principle. They are, in some sense, indispensable to make physics. Can you believe it's possible to do physics if you are not able to express a physical law in a way which is invariant on the reference system? Then there is no physical law, right? Can you think it's possible to make an experiment, to perform an experiment in a controlled way if you don't have a control of a local area, because instantaneous interactions from very far apart are allowed? So actually, I think that the principle of relativity, the two principles are really needed, otherwise you cannot do physics. They are indispensable for local knowability, local controllability. And to me, it's a very fascinating idea that there are other principles like that we still don't have recognized, from which we can derive quantum mechanics, so that the principle of the quantumness and the principle of relativity together are this kind of epistemological framework by which we can do just physics. Otherwise we cannot do experimental physics. So that's the idea. In this talk I will focus on finite dimensions only, and only on one kind of systems, in the sense that I will consider also multipartite systems, but made of the same kind of system. This simplification actually is totally relevant. If we are able to derive quantum mechanics in this way, in this case, then to generalize to different system is not an issue, and to generalize to infinite dimension will give additional problem, but anyway we'll have understood most of the problem. So we shall focus on finite dimension. Let me introduce now the operational framework. So it's just a probabilistic framework. So I will give you for granted the notion of probability in a way which is independent on your interpretation of probability, the notion of events that are just things that can happen, may happen. So we are really in a pure operational framework, so strongly Copenhagen, in the sense that everything should be defined by something that the operator can do. So everything should be defined. Every mathematical object should be defined operationally. And if two things are indistinguishable for the operator, because there is no mean to distinguish between them, then I will declare them the same. So identification of operationally indistinguishable things. And example of this principle are, as you will see, the notion itself of system, which is defined just as a collection of tests. Tests performed over it. The identification of events by their probability and by their conditioning, and the tautology that the set of state is, by definition, is separating for effects, and vice versa, the effects is separating for states, because if you are able, if two states are different, there must exist an effect by which you can discriminate it. So the fact that the sets are separating is part of this operational principle. Now, without deconsecrating completely the mathematical closure, let me just say that, at least in this context, if we go to field theory, the situation is different. But let me say that this mathematical closure is mostly for convenience. So, for example, as you will see, we will define the notion of sum, of transformations, and this kind of thing. That from the sum we can go to the difference. The difference is not operational, is operational, right? But then we take the closure, we have the linear span. So moving from the convex set to the linear span is a matter of convenience. It's just a matter of simplification of the mathematical framework. You have a mathematical framework which is implied by another one. It's just easier, then you use it. Norm closure, linear span, algebraic closure are mostly for mathematical convenience. The closure. And we have another kind of closure, which is the operational closure, in the sense that every option of the operator is automatically implicitly incorporated in the framework. Like, for example, the convex closure, we have this Peckens model. In this kind of toy models, if you don't have the probabilistic interpretation of state, then you really can say that there is no convex closure. But as soon as you interpret the states as probability rules, automatically you are forced, you cannot forbid to take the convex closure. And the same would be for the closure under cos-Gray. So these are the principles that will be taken in mind in this kind of search. Now, the postulates I'm going to show you are, the two of them are just part of the definition of cascade, and this is the no signaling from the future, and the definition of independent system. And this is the usual no signaling from things that are far apart, instantaneous communication. The first real kind of principle of quantumness, if you want, the first postulate is denoted by P-FAITHE, is the existence of preparationally faithful states. I will tell you what is this. Then I will also explore other postulates, the existence of a faithful effect, FAITHE, and PURIFY, the existence of purification for all possible states. We will see the consequence of these postulates. And then a stronger version of the preparationally faithful states. Recently, with Giulio Chiribella and Paolo Perinotti, we showed that these two postulates together give the Stein spring dilation. At the very end, I also will show you that whichever, because the search is not finished yet. So as you will see, I am pretty sure that from the previous postulate we just select quantum mechanics, but I was not able to prove it up to now. So we may need to look for other postulate or for a way to prove that it's quantum mechanics. And what I know is that in order to prove that it's quantum mechanics, we need a way to introduce the algebra of effects, which has no operational meaning. So we need an operational way of introducing the composition of effects. And a way to do that is to use a mathematical postulate, a mathematical isomorphism, which is the Choi-Jamolkovsky isomorphism, that, as you will see, using the atomicity of evolution, will allow us to identify effects with atomic transformation. And so we can compose effects using the composition of transformations. Okay, so let's start. The starting notion is that of test, like the tests of the test theory of Alex Wills, and the test is just a collection of possible events, things that may happen. In this case, there is a system which is entering this box, but we don't see the system. There is just the box, and there are these lights that are flashing, and which light is flashing is the event. And among all possible tests, we have also the deterministic tests that are the singleton test with one possible event. And what I want to stress that the same event can occur in different tests, and the probability of the event is not depending on the test. So the event is something that can happen if the same event occurs in two different tests, means that occurs with the same probability, independent of the test. Now, we can make unions of events. We can make the unions of all possible, let me be more precise. When I say events in this case, when I define the test, I should say that if these events are incompatible, then let's call them outcomes as usual, right? The incompatible events. If I if I take the union of all possible events in the test, then this will be a deterministic kind of test. We can take this union, and this union corresponds to make a new test in which two outcomes are unified in one new outcome. And this is the coarse graining of the test. And we can do the reverse in some cases, which is the refinement of the test. What is the state? This notion immediately entails the notion of state. The notion of state is just the probability rule for all possible events in any possible test, with the normalization over all outcomes in a test. That's all. This is the state. We will denote by this sigma, the convex set of states, is convex because we are in a probabilistic context. And here there is a convex set. As you can see, this convex set is not like a simplex. It's strongly convex. It's like the one that you have in quantum mechanics. And the states themselves can be regarded as tests, preparation tests. Now, this is the crucial point of all this talk. So this is the only thing that really is different from all different approaches, is the notion of cascade. The notion of cascade axiomatically is defined in the following way. You perform two tests jointly, A and B. This corresponds to a new test in which this B composed with A, this is a new test in which all possible outcomes are the joint outcomes, but if you take the marginal probability over the B, it will depend, it is independent on the test. If you take it over A, it will depend on the test. So there is this asymmetry in the marginal probability that depends on test A but doesn't depend on test B if you make marginalization on A or B. This is the arrow of time. This is the way in which we introduce the arrow of time. And this is not just, be careful, it's not just the Kolmogorov consistency, because this is the probability of A anyway, but the fact that this is an event is not a new event. It cannot depend on the test. This is the crucial point. And there may be different kind of cascade, like, for example, this one, you see in this cascade, suppose these are two machines with outcomes. If you connect them by a wire like this, and this is the system passing through, then you will have that the marginal, both marginals, depends on the test. So the cascade is a very special kind of composing tests. And the composition of tests will lead to a notion of composition of events. And this composition is closed under, is closed. You can compose as you want, and is associative. You have the identity. So it's a convex monoid because you take the convex closure. Because you can always, the operator is always the convex option in the probabilistic context. So this is what we call not signaling from the future, namely the notion of cascade, is crucial to define the conditional probability. Without it, you cannot define the conditional probability. The conditional probability is defined as the joint probability divided by the probability of event A. This is a new probability rule now for all possible events, D. So it becomes a state. So this is a state, the conditional state. This central dot denotes a variable event. Now, as you see, the evolution, the state conditioning is an evolution because it's what? The action of events over the state is just the joint probability rule with the variable event here. So we have identified events with transformation because of the notion of cascade. And automatically, this is a linear evolution. It's linear in omega. If you take convex combination, this is linear. And then if you take the linear span, it is linear. So we have seen that this notion of test entails the notion of states. The notion of cascade and signaling from the future has the consequence that events are identified with transformation and the evolution is state condition. Now, as I told you, we're really strongly Copenhagen. We want to avoid the notion of system because we don't see the electron, we just see machines, right? Is what the system is? A collection of tests. It's a collection of tests including states, preparation, that are just special kind of tests, which is closed under coarse graining, is closed under conditioning clearly, under cascading, and under convex combination. The closure under cascading is a very special kind of closure because means that we are considering only one kind of system. Think about it. There is one system entering a machine, then another system can come out. In this case, we cannot take this closure. So if we want to consider different systems, we have to give a separate rule on how to compose this test. Think to test as letters of an alphabet. Then the compositions, the allowed composition of tests is a kind of set of rules which makes this, the composition of tests, a language. And systems themselves will become language. So the most general framework is a language. It's not like your categories. How do you say? It's not a set of arrows. It's a language. Something more general, right? Well, anyway.
Language with cascading is a category, I would say.
Okay. Oh, it's a category. Yeah, I'm saying, yeah. There is this meta category in the beginning of the book. I'm just studying there, in which you start with a diagram with arrows only, right? And then it's hard to define if an arrow goes to a possible test and another arrow goes to a possible test and make a difference with the case in which this is a bipartite going to different systems. I don't know you can do by arrows. I think you need to use a kind of different concept, which is with the language you can do that.
The language should be your object.
Okay. Yeah. I'd love to discuss that.
Yeah.
Okay. So anyway, the situation with different systems is much more complicated. Now we have two equivalence classes for transformations. Two transformations A and B are let me say, conditioning equivalent if they will give the same state conditioning, for all possible states, and they are probabilistically equivalent if they occur with the same probability for all possible states. These are two completely separate equivalence classes that we call conditioning equivalence and probabilistic equivalence. And the transformation is completely specified by the two classes because the transformation is completely specified. So I will use the same word transformation as a synonym of event now. It's completely specified by the action over the state, over all possible states. So the transformation or events is completely specified by the two equivalence classes. What is the effect? The effect is just the equivalence class of all transformation occurring with the same probability for all possible states. So I will write the probability of the transformation is just the probability of its equivalence class, and I will use lowercase letter from now to denote effects, and I will write that the transformation calligraphic A belongs to the effect lowercase a, to say that this is the effect of the transformation, and meaning that the probability of the transformation is just the probability rule over the effect. And I will denote by this E the convex set of effects. I take the option of convex closure, clearly. And I will also use the action of the effect over the state instead of the action of the state over the effects, because they are just dual each other. The effect will be a bounded linear function over state, and the state is a normalized function over effects. I will denote by the letter E the deterministic effect, which gives the normalization of the states. So, if you just take by the rule of state conditioning, you will immediately see that the effect corresponding to the composition of events with the cascade is just the action of the transformation, linear action, over the effect. On the left instead of the right. So you have the Heisenberg picture. And then let me say that also effects can be regarded as tests themselves. So they will be incorporated into the system. If you take a complete set of effects corresponding to a test, they will be normalized to the deterministic effect. And this is just the notion of observable, generalized observable, like the notion of P of n in quantum mechanics. So we have seen that from this identification of events as transformation and evolution as states conditioning, starting from the cascade notion, we are getting the notion of effects and the notion of observable. Now let's see, we can make addition and rescaling of transformation. The addition is just the fact that you can have two transformations occurring even in different kind of tests, in different tests. But suppose that the sum of the probability for all possible states is smaller than 1, then in principle they can occur on the same test. So we say that they are test compatible. Then you can make the union of these two as if they were in the same test. And this is just the sum of the two. And this the sum is just defined as the sum of events over the state. This defines completely the transformation, because you just need to know the action over all possible states. It's just the sum of the two transformations acting each one over the state, which is the same as having this probabilistic equivalence class, which is the sum of probability, and the conditioning class, which is just the convex combination of the two conditioning. So, you can define a rescaling by just saying it's the new transformation which gives the same state conditioning, but which occur with rescale probability. And now I can define what is an atomic transformation. An atomic transformation is a transformation that cannot be decomposed, cannot be refined non-trivially, as the sum of other transformations that are, at least one of them, not proportional to A. Okay, so these are the atomic transformations, the one that cannot be refined. And I want to emphasize that the identity transformation, if you take the probabilistic framework of classical mechanics with orthogonal states, is non-atomic. So the identity transformation usually is non-atomic. In the quantum case, it is atomic. So we will take a convex cone and linear spans. We put the plus for the cone. The T will denote the convex monoid of transformations. T plus the cone of transformation. And then we'll take the linear span over the complex and over the real. And we will say that the convex cone of states is the dual of the convex cone of effects, because we are taking the option of the convex closure, and we say there is no limitation to preparation. This is the case. Now, what does it mean to have an observable which is informationally complete? It's just an observable which spans the linear span of effects, and a set of states which is separating. It's just a set of states which spans the linear span of states. You can have both things together in a single test, which is what Chris Fuchs calls the Quantum Bureau International Deploy and Measure, in which the observable is informationally complete, and each state reduction is a state of a separating state of states. Separating set of states. That's just a curiosity. Now, you see, transformation acts linearly over effects or over states. They can be represented as matrices, real matrices over. And you can define, since we are in finite dimension, the linear space you can take as an Euclidean space. Take a scalar product. You can define an adjoint over the scalar product. You can make this, you can close over the norm coming from this, and you can get this as a sister algebra. We will see that, by the way, there is an operational way of defining the scalar product, and there is an operational way of getting the adjoint also. So, everything comes out from one simple idea. This is the starting point, the notion of cascade. And you have a matrix algebra. Now we have the notion of independent systems. We say that two systems are independent if you can perform all their tests as local tests, in the sense that they commute, namely if you perform first A and then B, or first B and then A, you get the same. Now, since now this notation is redundant, I can just put in a row all local events. So I move from the single system to the Cartesian product of systems, putting them in a row, and the corresponding effect of a local set of events will be just the Cartesian product, so a list of local effects. Now I define how to compose system in a very simple way. I take the system, which is the collection of all possible local tests, and then I put additional tests, and then I close under cascading, under complex combination, under coarse graining. And this is a new system which includes some tests that are the local tests, and other tests, the complementary ones, which are the non-local. That's all. Now, the states over the composite system, let me call this multipartite state, I can take the marginal over one specific system. This is the marginal state corresponding to the partial trace over all system apart from one. Means what? Just that I take the probability rule corresponding to perform the transformation A over system N and just the identity over all other systems. In terms of effects, this will correspond to have the deterministic effects everywhere apart from the local effect here. But the deterministic effect can come out from any complete test. So this is just the no signaling. Any local test on a system is equivalent to no test on an independent system. This is the no signaling. So no signaling is tautologically the same thing as defining local test, which is tautologically the same thing as defining independent systems. They are synonymous. So, what is a probabilistic theory? The general framework is just a matrix algebra, right? Over transformation over effects or over states, if you like. An independent system is no signal. And you have this Cartesian product only for the local test. So we need to find the mathematical representation of independent system. Let me review very shortly the notation. Sigma, E, and T transformation, the cons with the plus. The system is a collection of tests including states, lowercase Greek, and effects, lowercase Roman, and the variable denoted by the dot, the action of the transformation of the state is the joint probability rule with next forthcoming event. Belonging to an effect means that this is the effect of the transformation. E is the deterministic effect. Bipartite, I have this central dot. If they are the same system, I take the square central dot. So the uppercase Greek will denote joint states, and the uppercase Roman will denote joint effects. And for example, if I put 1 and 2, this means that this transformation acts on two systems, 1 and 2. And if I put in this way, this is a local transformation over system 1. And is the identity transformation. So here are some examples. This is the same to say that the probability with the state omega of effect A, or the action of effect A over the state. Here we have an example. This is the Stein spring. So we have the joint transformation U acting on omega and sigma, and then we take the partial trace over system 1, namely the deterministic effect here. And then we get that this is equivalent to the action of a transformation over the state. So this would be the statement of the Stein spring. And here we have the action of an effect over the system 2 and 3, and this is joint state phi over the system 1 and 2, and this is state omega over system 3. And this is equivalent to a new state. This looks very close to your category.
You're using the language of Mauro.
Yeah, but up to now there is only one kind of system. That's not the trivial thing. We want to discuss that with you. So this is we take just an effect and then we get a state. And this is actually the most interesting kind. We will see this many times. So we take an effect, leave the other variable. This is a state. This is going to be used a lot. So what is a faithful state? This is the central notion. It's bipartite state. I call it dynamically faithful when the output, which is the action of transformation, local transformation A over the joint state, is in one-to-one correspondence with the transformation. This is a crucial thing because then I can, from the output state, I can calibrate my test. So this is what you need to make test calibration. Then I have the notion of a preparationally faithful state, which is just that I can achieve all possible joint state by a local transformation over this preparationally faithful state with non-vanishing probability. And this is the possibility of preparing all states by just a single state with local tests. Postulate is the postulate P-FAITHE, that for every couple of identical systems there exists a symmetric, means invariant under permutation of the two systems, state phi, that is preparationally faithful. Simple theorem, just because it's a map which is surjective, a linear map which is surjective is also injective in finite dimension, because this is true in finite dimension. The theorem says that if phi is preparationally faithful, then it's also dynamically faithful. So we got two pigeons with one stone. Now let's see all the consequences of this postulate. So we have seen we can make calibration of test and preparation of states by a single state, by local test. There is the impossibility of secure bit commitment. I don't know how many of you are do you know about the bit commitment. In this case, impossibility means either that there is no concealing protocol, or that if it's concealing, then cannot be binding. Then, this is something which looks very quantum. The marginal state is a state which is internal, inside the convex set. Namely, you can write this state as the convex combination of any state with other things. It's like infinite temperature state is like the center of the convex. Actually, not really in the center, whatever is inside the convex. And is invariant under the transpose of the deterministic test. We see now what doesn't mean transpose, but this is exactly what you have in the usual algebraic framework of quantum mechanics. Crucial consequence is the local observability principle, namely that there exist global informationally complete observables that are made only of local informationally complete observables. Means that you can make the full determination of the joint state of any number of systems. Not, in order to do that, you don't need a new machine for every number of systems. You just use the same machine many times locally. This is a huge reduction of experimental complexity, and is something that is really should become more popular, since so many people write a popular book about, you know, these stupid scientists. They are still reductionists, but we know that nature is holistic. And what does it mean? Reductionism is just because you have this local observability principle. So even though nature is holistic, we can work in a reductionist way. Other consequences. So I will use this symbol for the field of real or complex. This is just the trivial definition of preparationally faithful state. There is a linear isomorphism between all possible transformation and all possible joint states. This is the most important one. You have a weak self-duality. So what does it mean? If you take the faithful state and you just make a local effect, this will give you a state, and this is a one-to-one correspondence between the two cones, the cone of a state, the states and cone of effects. But we say that the two are isomorphic in the sense that there is a linear map between their spans which preserves the cone in both directions, namely is also surjective over the cone. This is the crucial point. It's easy to get it in a way which preserves the cone but not in the reverse direction. That's the real problem, that it is not surjective in general. In fact, we will see this now. For other things. Yeah, then we get immediately that there is a tensor product representation for the linear span of joint states and linear span of joint effects. And also that the transformation, the linear span of transformation, is the full algebra, the full matrix algebra is complete. The full matrix algebra over effects. The faithful state as another consequence is that it provides you a kind of a physical definition of the scalar product, in the sense that the state is symmetric. This is just a triviality of the fact that I just choose it as symmetric. It's symmetric. So you can always take the absolute value of the symmetric form by the Jordan decomposition of the positive and negative eigenvalues. So this denotes the Jordan evolution, the one that changed the sign in front of the negative eigenspace. Right? So it will give you the modulus of the form. So now it's a positive form over Fs, which gives a scalar product. And this Jordan actually is the equivalent of the complex conjugation. And you can define the transposition, because since the state is dynamically and preparationally faithful, for every local transformation there is an output state, and for every output state there is another local transformation on the other system which gives the same. So this is the operational definition of a transpose. You can immediately check that you get the composition of transpose in the reverse order. So you have both the complex conjugation and the transpose. So you see how many things this postulate gives. The marginal state, which is internal and invariant under the transpose, is the same as in quantum mechanics of a channel. And the local observability principle, the tensor product rule, the scalar product, the transposition, weak self-duality, calibrability and preparability, impossibility of bit commitment. But this is not quantum mechanics. It's much more general. And I know that. So we need to find other postulates, unfortunately. So let's explore this 2-1, postulate FAITHE, faithful effects. So remember this one-to-one correspondence. This is an isomorphism between it's really an isomorphism in the sense that extremal rays to extremal rays and convex combination to convex combination. Now, this is, since the state is faithful, this is an invertible matrix. I can take the inverse of this state, which is not generally an effect, if I assume it is an effect. So I assume there exists an effect, a bipartite effect, which achieves the inversion, which gives this rule. So if you compose the state omega E here, you get the effect E. Then I can prove, okay, this is teleportation. Okay, because this occurs with some probability, it's the probabilistic teleportation. I can prove easily that then F is also faithful in the sense that every possible bipartite effect is just the local evolution of this effect. And realize the cone isomorphism between the joint effects and the transformation. But it does not realize, okay, there is some, sorry. It does not realize the isomorphism between the joint states and the joint effect for a very subtle reason. So this is very subtle. It sends so let's do the following. Take this one. So I have now two states, so it's a four-partite system. I take an effect over system 2 and 3, the central one here. This is a joint state, right? And very easy to see that if you have a separable effect, you get a separable state. So this sends the whole cone of effects into the cone of states and sends separable to separable. And since this is a bijective map, it sends non-separable to non-separable, but it is not generally surjective. So they may be here separable, non-separable states, only non-separable states that have no corresponding non-separable effect. So we don't have this, that if you take two faithful states together here, then you get a new faithful state for two systems and two systems. say I was unable to prove, but I think that I was unable to find a counterexample, but I'm sure there is a counterexample. So this is a much stronger version, which I'm going now to consider. An interesting thing I want to stress is that this probability of teleportation probability is actually, if you maximize overall possible effects, it is a property of the theory. So you can classify Popescu-Roerich, whatever, quantum and classical, with this probability. Or you can have a probabilistic teleportation in the classical case. It's not very surprising. And in quantum mechanics, this is just the inverse square dimension of the system, of the Hilbert space. And this cone isomorphism is the Jordan involution with this constant. This is what you have in quantum mechanics. And indeed, if you compose the faithful effect with the faithful state, you get the identity, and the identity is the absolute value of the faithful state. It's the maximally entangled state. Now, I am exploring another postulate. This looks, and I think, is pretty ad hoc. So it's just to understand what's going on. Possibly, it may be possible that I can prove it, but I was unable to. That may be, from the previous postulate, every state as a purification. I was not able to prove it. Then let's consider what happens if every state has a purification in a bipartite state. All these things happen, that each state can be obtained by applying an atomic transformation to the marginal state. This is like the square root of the effect in quantum mechanics. Each effect contains an atomic transformation. This is really non-trivial. The identity is atomic. You can prove that. This is not easy to prove. It's mathematically simple, but the logic is not easy. And this is only quantum. You cannot get this in classical mechanics. This is only quantum. And I really suspect that it's just quantum mechanics. But you know, we are assuming purification of all possible states. It's a very quantum thing. And the state, phi, the faithful state, is pure, which is quantum. In the classical case, is mixed. So, as I was saying, we would love to have that if I take two faithful states, then I get a new faithful state for system 1, 3, and 2, 4. So if I take many copies of the faithful state, then I get a big faithful state for system even, odd, and system even. So this is a new version of the P-faithful, which we call super-faithful. And we analyzed the consequence of this postulate with Paolo Perinotti and Giulio Chiribella. And if you put together this with purification, then you can prove fate, the existence of a faithful effect, and also Stein spring. Okay, there is an additional thing that you have, this is really pretty ad hoc, I'm saying, that all purification are connected by local automorphism. I didn't mention that by just taking the very general mathematical framework of the probabilistic theory and nothing more, you can prove so many things, like contractivity of channels, like that isometric transformation of effects or of states are automorphism and things like that. So things like that, they are very close to what you have in the classical and quantum case, like unitary transformation, isometric, and automorphism, and many other things. So here you can prove that you get the Stein spring. But as we have seen, it's very close to the quantum case. Actually, I am sure it's quantum, but I was not still able to prove it. So it's just that it's hard to prove. So what is this something more? I don't know. It could be just preparationally faithful and faithful effect and purification, or the super-faithful and purification. In any case, what I want to show you now, that if we want to prove it, we have a forced, obliged step. We want to find the composition of effects. Because the peculiar thing of quantum mechanics is not that transformation make a system algebra. This is obvious. Is that effects make a system algebra. But effects are equivalence classes. Probabilistic equivalence classes of transformation. What does it mean to make the composition of them? There's no meaning. So the only way to define the composition of effects is to have a kind of, bijection with transformation, because I can define the composition of transformation. And this can be done using the Choi-Jamotkowski isomorphism. So if I really want to derive quantum mechanics, I should have a way that, I give you the probability of the lab, and then you write the operator, what I call reconstructing quantum mechanics from probability. This is going to be, by the way, this is the title of a new meeting at Perimeter, reconstructing quantum mechanics. I think it's very nice. And so this is a paper we wrote many years ago, 2001, about tomography of operators. So you want to measure the operator which transforms a state into a state. You want to have all matrix elements. What you can do, you get all matrix elements, really, apart from a phase factor. But you need an assumption. You need to know that the transformation has the Krauss form. And in the case of a single operator, you need to know that there is only one term of the Krauss form. So it's an atomic transformation. But in order to know that it has the Krauss form, you need to know that the transformation acts over effects, because you can compose effects. And one way to do that, one way to introduce the composition of effects, is to have this Choi-Jamotkowski isomorphism, which is just a one-to-one correspondence between the transformation, this is the cone of transformation, and the cone of positive bilinear maps over complex effects. This is a cone isomorphism in the sense that is a linear map, invertible map between the two linear spans, and sends cone to cone and vice versa. Now, clearly, you can identify the atomic transformation with the rank 1 matrices over effects, which are just the effect, apart from a phase. There is just a phase. So you can, then, if you compose transformation, you want to get, if you compose atomic transformation, you want to get another atomic transformation. This is not obvious. Because what does it mean? That if I have two atomic transformations, yeah, I cannot decompose them, right? So I compose them, then I can. Maybe there is another test in which I can. So, another assumption. Okay, let's take atomicity of evolution. Okay, atomicity of evolution. And now we can prove that the phase is really trivial. And we can even define, we can take the so-called polarization identity to define the effect in terms of the transformation in a way that you can compose transformation and get effects, the composition of effects. So, if you have this, you can reconstruct quantum mechanics. But there is no meaning for the composition of effect. And there is no meaning for these bilinear forms over complex effects that is in correspondence with transformation. Why? I thought a lot of things, we can discuss that. No way. So, but if we want to prove that the previous things is quantum mechanics, we need to pass through these forche caudine. Now, summary. I'm finishing. We have seen that this notion of a cascade, which is the central notion of all this approach, gives this identification of events as transformation and evolution as conditioning. We have seen that the whole probabilistic framework is just a system algebra of transformation, and independent systems, the notion of independent system is the signaling. This preparationally faithful state is a very good candidate, especially the stronger version, the super faithful, because it gives a lot of things. a lot of things like weak self-duality, like impossibility of recommitment. Which, you know, this is not a trivial thing because Clifton, Bubb, and Alvorson use this as a postulate, let me say, not very clever, to get quantum mechanics, but they didn't, because they assume quantum mechanics. Everybody knows. So you get scalar product, transposition, you get the complex conjugation as the Jordan involution, you get the tensor product, this strange property of the marginal state, which is internal and invariant under the transpose of a channel, all these things. But still is not quantum. Here you have both classical and quantum. At least. I would be happy if I get quantum and classical, it's finished. The program is finished. If I take this faithful state, yeah, this is equivalent to teleportation. It's probabilistic teleportation. If I take the purification postulate, then I have many other things. This is typically quantum, that the identity is atomic, and the faithful state is pure. And then finally, I show you that if we really want to prove that something is quantum, we need to find a way of defining the composition of effects. Thank you for your attention.
You've also kept very good time, so we have time for some questions.
Right, so it's obvious, like, there's tons of similarities, and
Yes,
this basically begging to be formulated in monoidal category, because your fate is actually the compactness we use.
Yes. In fact, I'm very excited. I'm studying your papers. I want to see.
Yeah, so Peter Salinger, for example, did quite a bit of work on how George and Markovsky relates then to having compactness as a primitive and that you can generate convexity. So, but the thing is, in sort of part of the way we play the game, we only take the tensor and we don't assume anything like probabilities in a priori. And the game we have been playing is how far can you get just with only that.
Yes,
And
yes.
so it would be nice to see how the blend of this one.
Yeah, actually, what I would love to do is to build up an operational category and then add a functor to your category. This is what I want. This is the solution of the problem.
Any more questions?
Mauro, could you indulge me a little in answering what's probably a very stupid question?
No.
If we go back here to the slide where you define the scalar product that comes from.
Yeah. Scalar product. Yes. This one?
I think so. Let's see. Yeah. So, I mean, I see why that's giving us a nice symmetric bilinear form, and I see why it's positive on positive effects, but I don't see why it's. Are you claiming that that's an inner product?
Yeah, it's positive.
For arbitrary A and B, not just positive A and B.
No, this is why I need to take the absolute.
I understand.
Otherwise, it's not positive. The state is positive over real effects. If I take the linear span, it's not positive anymore. That's why I need to take it symmetric, so that I can take the absolute value. Actually, I can even take it non-symmetric and take the polar form.
Sure.
But the polar form makes everything messy. And, you know, there are two identical systems. Let's take it symmetric. It's obvious.
So this Jordan involution is just taking B. If we think of B as you know, B plus minus B minus, this gives me B plus B minus. If these are the positive and negative.
Yes,
parts.
if it is the negative, it changes sign. Right.
So if I have.
There is also a theorem by Giacomo, I think, that if you have a convex cone, the composition and difference of cones is unique if you have a Euclidean structure, if you have a scalar product over it.
If it's got a unique Jordan decomposition.
The Jordan
then
decomposition.
it's self-dual.
Yeah, then it's self-dual,
Yes,
right?
Yeah.
Because in that case you have just a single.
Right.
Euclidean space.
Maybe you show me afterwards. I understand.
Anyway, this is just the fact that the state is positive over real effects. But when you take the linear span, it's not positive anymore.
Right.
Then you need to find the positive, the absolute value. And this will give a real scalar product, which is positive. Then you can extend to complex. So everything is defined. When you start from real, and then you put I and take the complex. That's another thing. But the problem is you need something which is symmetric and positive.
Okay, well, I'll ask you more later.
Same point. I think we need some explanation there sometime later, or
Yeah.
we can give that later in more detail. Because it looks a little bit circular, right? In order to, you want to define a canonical scalar product, right? Up to that point, you just invented one.
Yeah.
And
Yeah.
whatever that gives you. But now you want to really define a canonical one. And but in order to define the absolute value
Right.
of a form, you already need a scalar product.
No, because this is a linear. No. Okay. Wait a minute.
For the
This is-
composition, you need an adjoint.
No. You just take a this is a matrix. You just take any basis you want in effects, and then you have a matrix, and you take the positive form of the matrix. It's a symmetric. It's a symmetric matrix. You take the positive, the absolute value of the matrix. That's all. You don't need any scalar product.
Okay, we'll do this.
You say there is always a canonical scalar product in your mind, but it is not. It is not that.
in your mind, but it's not canonical.
Okay. If you are in finite dimension, every linear space is Euclidean, because you take just a basis,
Sure, but then it depends on the basis.
and then you say this basis is orthogonal, and then that's all.
Sure, no, it's not so simple.
Yeah, but this is not what I do here, because what I do, I have a matrix which comes from the fact that here I have a bilinear form. So to each bilinear form there is an associated matrix, right? And then I take the absolute modulus of the matrix. And this is the absolute modulus of the form.
Okay, let's look at that later. I think there is a depends.
Any other questions?
You show that one of the consequences of your P-FAITHE is the local, how did you call it?
Local observability principle.
Observability principle,
Right.
which you argued is equivalent to the notion of reductionism. Is
The
that
notion of what?
reductionism? You said that.
Right, in the sense that you can make local experiments to know everything.
Right. That seems to me a pretty strong and also quite intuitively appealing consequence.
Yeah.
And I'm wondering whether you could also take that as your starting point.
Oh,
Rather
okay.
than
Yeah,
the
I thought about it's you just get the tensor product if you use it as starting point. So it is weaker than using this faithful state.
So it would not be sufficient.
So, for example, there is a work by what is the name of this mathematician? The girl invented wavelets. Davishi. Also, she wrote. Sorry, she wrote a paper in which she showed that if you assume this principle, then you get the tensor product. Otherwise, you can have both tensor product and direct sum. But then there is the work of Rayner, that there is always a way to embed inside a tensor product. So, in some way, because once you have C-star algebra, right, then you embed in a tensor product. There is always a tensor product. The only problem is that if you use this in the operational case, then you need to extend effects. So you need to add additional effects that may be non-physical. So if you allow more effects, this principle is always true.
So you're saying your P-FAITHE implies local observability, but the reverse is not true.
No, reverse is not true.
What
No.
do you need in addition? If you take local observability as a starting point, what do you
Because
need in addition to?
that's very simple, because the preparationally faithful state is much stronger, because it does not give just a principle of information that you can get, but also a possibility of preparing states, which is more than just getting information. It's much more.